Hello everyone. Now I am going to explain about tensile test on mild steel. In tension test, ends of test piece are fixed in the grips connected to a straining device and to a load measuring device. The test involves straining a test piece by tensile force generally to fracture for the purpose of determining one or more of the mechanical properties. The straining unit of universal testing machine consists of a main hydraulic cylinder with robust base inside and piston which moves up and down. This is the UTM machine, universal testing machine. The lower table connected to main piston, okay, through a ball. The ball seat is joined to ensure the axial loading. There is a connection between lower table and upper head assembly that moves up and down with the main piston. The control panel consists of power pack complete and complete with the drive motor and an oil tank, control valves and an autograph record also is there. The load indicator system consists of a large dial and a pointer. A dummy pointer is provided to record the maximum load reached during the test. Load is applied by hydrostatically lubricated ram. Main cylinder pressure is transmitted to the cylinder of the pendulum dynamometer system housed in the control panel. The cylinder of the dynamometer is also self-lubricated design. The load transmitted to the cylinder, the dynamometer is transferred through a lever system to a pendulum. Displacement of the pendulum actuate the rack and pinion mechanism which operate the load indicator, pointer and the deflection of the pendulum represent the absolute load supply on the test specimen. Return moment of the pendulum is effectively damped to absorb the energy in event of sudden breakage of the specimen. This is a stress strain graph of mild steel is divided into 4 areas in which first section represent elastic deformation and in the remaining areas of only plastic deformation will take place. However, there are 4 different sections represent here in this strain diagram. Actually, this is the second one is yielding, third one is strain hardening and necking. The final point is fracture. This is ultimate stress point. Okay, so here area B. Okay, so this is A, B, C, and D and E is there. With respect in this graph, area B is define the flow region. Here the material is stressed beyond the elastic loadability, and with the flow region the stress changes very irregularly with increasing strain. So that wave line result in the graph. Next one is section C. This is section C. In this section the stress increases sharply and the plastic deformation also increases. At the maximum loadability, the materials, the cross section begin to reduce in size and ultimately failure occurs. Increase sharply and the plastic deformation also increases. At the maximum loadability, the materials, the cross section begin reduce in size and ultimately failure occur. So elastic deformation, it is represented the capital A. This is the first phase of stress strain damage is elastic deformation. Already you know very well elastic deformation means once the load is applied on that material, it is changed its original position. After release of load, again it comes to its original position. That is called elastic deformation. When the stress acting on the material is removed, the material regains its original length. That's already mentioned. This is called the complete recovery or resilience. Again, the area of elastic deformation is divided into 2 phases. In the first phase, the material stretches proportionally to the stress acting on it. This extension is also called linear elastic or proportional deformation. The point at which the linear elastic deformation is maximum is called proportional limit. See, this is called proportional limit. Beyond the limit, elastic deformation still take place. However, the greater elongation occurs in the section under increasing applied force. Therefore, the elongation or strain is greater than the increasing stresses. Next one is this is the B, the flow region B. Further, small increase in stress can be enough to cause the proportional limit to be exceeded. The highest flow point is the point accompanied by the initial sudden loss of quality. As a result, the stress required to continue to elongate the material reduces immediately and reaches the lowest flow point. After these points are executed, even if the forces are removed immediately, the material does not regain its original properties. When the stress is increased again, the dislocation starts to wander and increases, which leads to further quality losses. The first two flow point, the stress strain behave irregularly in relation to each other. Next one is this is the C. So this is called material hardening area. If the stress is increased further in increasing number of upright dislocation formed in the crystal lattice prevents the movement of previous steel sliding dislocation. At the same time, the stress in the crystal lattice continues to increase, which causes hardening of the material. Here the metal becomes stronger as the strain increases, hence it is called strain. This is called strain hardening. In this area is strain hardening. Okay. So in case which cause hardening of the material, it is called as strain hardening. However, the process cannot be continued infinitely. Each material has its specific maximum force. If the maximum forces is exceeded, the material begins in the crystal lattice of the metals bar. So many dislocations have occurred that can no longer lead to hardening, but instead contribute to the formation of voids or cavity. See, this is a lot of cavities and this cavities and blowholes are there. Okay, and apart from necking, the voids also cause a metal cross section to reduce. The stress now act on increasingly smaller cross section, which enhances the process still further. As the tensile test continues, the necking increasing until the tapered cross section can no longer withstand the stress. This when the metal bar tears at the weakest point. Finally, the specimen will have increased length and reduction in the cross sectional area. So normally, how the stages of the ductile fracture? See, this is the ductile fracture stages. The failure of the ductile material under tensile loading can be attributed to cup and cone fracture. See, cup and cone fractures. This form ductile fracture occurs stages that indicate after necking. First, small micro voids there. Small micro voids form in the interior of the material. Next, deformation continues and micro voids enlarge to form cracks. The crack continues to grow and it spread laterally towards the edges. See, lateral towards the edges of the specimen. Finally, the crack propagation is rapid along the surface that makes about 45-degree angle with tensile stress axis. The new fracture surface has an irregular appearance. The final shearing of the specimen produces a cup type shape on one fracture surface and cone type on adjacent fracture surface. In this central interior region has an irregular and fibrous appearance, which signifies plastic deformation in material. So this is the detailed and important information on the mechanism of fracture can be obtained from a microscopy examination of fracture surfaces. This study is known as fructography. See, this is a fructographic study. Okay. Variation of local elongation with position along the gauge length of tensile specimen. In this graph is represents x-axis gauge length and y-axis lateral elongation. So this is after elongation specimen. The measured elongation from the tension specimen depends on the gauge length of the specimen or dimension of the cross section. This is because the total extension consists of two components: the uniform extension up to necking and the localized extension once necking begin. Okay. The extent of uniform extension depends on the metallurgical condition of the material and the effect of specimen size and shape on the development of the neck. The shorter gauge length, the greater is percentage elongation. Okay, this is a universal testing machine. In this testing machine, only using purpose for to find out tensile test on a given specimen. Now, I am using mild steel rod. Okay, this is the overall control unit. This is as a switch, control switch, on and off switch, and this is hydraulic supply. So in this control unit is connected to in this jack. Okay, when you are going to apply the load, what will happen in this elevator screw will be lift up or lift down with the using with the help of in this button. You can move up or move to up or downward direction. This is the main gauge. Okay, the capacity is 400 kilonewton, but now I am fixed 400 kilonewton. This is a null position. Here mentioned, shown there are two different pointer, one red and white color. The white color only indicate at the time of during that at the time of during load, indicator will be moved like this. Okay, in this white pointer is guided to in this replay indicator. Okay, here per division, see, so 0.8, so per division is 0.8. Okay, so per division is 0.8. With respect to fracture load, we can observe the values from in this gauge. Okay. Okay, this portion is backside of the control unit. This is the hydraulic unit. In this hydraulic unit only supply the load to the elevating screw. Okay, so this is the load. With in this load only you can adjust based on your requirement. You can adjust you can adjust in this load. So whatever we need load, we can adjust with the help of in this load position. You can easily adjust the pointer load. Okay. So now I can switch on. Okay. Just to see, the limit screw will move up on. It's move up and down with respect to your requirement. Okay. Actually, this is the working table. Here there are two grippers are available. Okay. This upper gripper, here lower gripper. The UTM, the tensile test specimen fixed in between the two gripper. Okay. By using with the help of this handle. This is the tensile test specimen. See, okay. This is the tensile test specimen. Now I need to measure the initial dimension for in this particular specimen, length as well as diameter also, by using with the help of vernier caliper. Okay, and this in this part name is extensometer. This is dial gauge. You already know here there are two dials here available. One is small, another one is bigger one. Okay, so in this dial gauge is fitted in this extensometer. In this extensometer is connected to the specimen, Actually, this is the experimental setup. Once measure the gauge length and diameter. The specimen is fixed into one gripper, and then one more gripper, bottom gripper is not fixed. Now I am going to fix. Okay, just I can switch on. See, the lifting screw lift up. See, so now the position so now the specimen exactly fitted both the end grippers, okay, tightly. This dial cage also exactly positioned, okay. Now I am going to adjust null position. Okay, the elongation will happen here. Yes. Next 20. So every 10 division we can observe the value. So now okay, now is over. Now switch off the machine. Okay. This gauge, this is the ultimate fracture load. Okay, this is a final load. Okay. So in this final load, should observe. Okay, this is an ultimate fracture load. Okay. So now the experiment completed. All the values are observed and tabulated. So this is a failure specimen. So now I am going to remove the specimen from in this experimental setup. Afterwards, we can measure what is the exact gauge length and what is the exact neck diameter. Okay. Failure specimen. Okay. Already fractured. So now I am going to measure the final length. See in this diameter, this is the cup cone diameter already told. Okay, this is a cup cone fracture occurred. Now I am going to measure the final gauge length and the final diameter of in this component dimension. Okay, now I am going to measure. Okay, now observe the value. Now I can do calculation part, and this is specimen initial diameter at small d1 is equal to 12.81 and d2 is equal to 12.82. Two values are already measured with the help of vernier caliper, and average initial diameter is d is equal to 12.82 mm, and length of the specimen between the gripper how much means here 192 mm, and distance 2.5 d is equal to 2.5 into 12.82 is equal to 32.05, already marked on specimen. This is tensile test tabulation. The load in kilonewton, the first column, and the second column extensometer reading in division, and third column IVD scale reading in mm. So all the three values are tabulated. So final IVD scale reading is 33, and extensometer reading also tabulated. Next, go for a graph. This is a load based IVD scale reading graph. X axis represents load and y axis represents IVD scale reading. In this graph plotted with respect the tabulated reading only. Okay, so from this graph we calculated yield point as well as ultimate failure load point. The next graph is load based extensometer reading. X axis represents extensometer reading in division, and y axis represents load in kg. All the values are marked in graph. The finally got slope value. So delta x, delta values are 55 and 12.5. The slope value is equal to 2.27. After complete the experiment, to calculate final diameter of the specimen, the dimension is 7.86 mm, and final length between the punch mark is equal to 85 mm. Then this is the observation, final observation. So initial dia in mm is equal to 12.8 mm, already measured, and the length of the specimen is equal to 192 mm, and punch mark at interval of 2.5 d in mm, how much means 31.42 mm, and final length between the three punch mark in mm is equal to 85 mm, and final diameter in mm is equal to 7.86, and original cross sectional A0 mm square, how much means 129.02 mm square, and final cross sectional at neck in mm square is equal 48.5 mm square, and least count for dial gauge 0.01, and average length of extensometer in mm, how much means 120 mm. So based on in this observation detail, we can calculate main calculation. This is main calculation. Yield stress, the formula is load at yield point by A0. The load at yield point values got from graph, the 43 kilonewton, and A0 value already found 129.02. The answer is 333.28 Newton per mm square. Then tensile strength, this is very important. So tensile strength, the unit is Newton per mm square. The ultimate load by A0. In this ultimate load also found from graph only, 42 kilonewton divided by 129.02. The answer is 379.79 Newton per mm square. Then modulus of elasticity gigapascal, the formula is slope into 1 by least count into gauge length divided by A0. So all the observation values are substituted in this formula, then calculated. The final answer is 211.13 gigapascal. Afterwards, percentage of elongation is 35.26, and percentage reduction area is equal to 62.41. So this is the final answer. Okay, thank you. For compressive strengthened specimen, procedures are same, and calculation procedure also same. The only difference is the load applying. The load is applied to specimen downward direction. Okay, thank you.